I want to go through just a little bit of the instrumentation amplifier, just to sort of re-emphasize some points and make it kind of clear. So, or hopefully make it a little more clear. So we've got these two stages, basically. We've got these non-inverting configuration, two non-inverting configuration amplifiers, one for VI1 and one for VI2. And then we've got, and the job of these is to boost VID above VCM. So to boost the differential input voltage above the common mode voltage. And then there's just a simple, straightforward difference amplifier, which we've looked at just before. And its job is to eliminate the common mode. That's all it really needs to do. And because we've got these so because we've got those resistors, the R1s, if we've called it a single value of 2R1, we've got a common current flowing through here. Now note, this is not the same current here and here, right? Those two currents are different. And again, over here and over here, these currents don't add up to this current here. They're different currents, but what we do know is that in that feedback resistor R2, both of these share exactly the same current. So when there's mismatch between these two resistors, we kind of automatically take that into account. And we have just a single resistor, R1, which we could use to adjust the gain, for instance. And the important thing to notice right now is that because this is the inverting configuration, or non-inverting configuration, but we have negative feedback, the virtual short is active on the inputs. And so that means we have VI1 showing up there, and we have VI2 showing up here. So that means between, across this resistor, we have VI2 minus VI1, and that's making this current I. So because that current I is created by that resistor, 2R1, which is shared by both of these difference amplifiers, that's where some real power, the real strength of this system is. That negative feedback, another way to say this, is making VI2 show up right here and VI1 show up right here. And it makes it easy to find this current. I'll just call it I right now. I is equal to VI2 minus VI1 divided by 2R1. And that would be the same as VID over 2R1. And remember, 2R1, if I said it was equal to 1K, then that value of this resistor here is 1K. Don't be dividing it by 2 or anything like that. So we could find these values here, V out 1 and V out 2, because that's what the op amp will be, those op amps will be producing. So V out 2 is equal to VI2 plus I times R2. And V out 1, or I could write that as VI2 plus the input differential voltage, VID, divided by 2R1 times R2, right? Because that's the value I had here. Just substitute that in for I, and we get that. And by the same path, we have V out 1 is VI1 minus VID over 2R1 times R2. And then if we look at the difference between these, And that's the input of the difference amplifier, right? So this whole thing here is a difference amplifier. So V out 1 is right here, and V out 2 is right here. Those are the inputs of the difference amplifier. And if we look at that difference between them, V out 2 minus V out 1 would be equal to, I'm going to have to make a little room for that, VI 2 plus VID over R. I'm just going to write that over down below because I don't have enough room. Okay, so V out 2 minus V out 1. Those are the inputs to this difference amplifier, the second stage. Would be VI2 plus VID over R2 over 2R1 minus VI1 minus VID times R2 over 2R1. And so we then have, if we simplify that, we've got VI2 minus VI1 and plus this and this, that becomes a plus VID R2 over 2R1 plus VID over R2 over 2R1. And that just simplifies to, so this value here is VID, right? That's the differential, the input differential voltage. So we have VID times, wait, okay, I'll write that out a little bit. We've got VID plus VID times R2 over 2R1 plus R2 over 2R1. And we've now got two VIDs, so we can actually write this as 1 plus, write that as VID times 1 plus that quantity there, which is actually 2 times R2 over 2R1. So we've got 1 plus 2 times R2 over 2R1. You might have to kind of work that yourself, but anyway, hopefully that's clear enough. So the difference between these two inputs to the difference amplifier, that difference between this node and this node, that difference is right here, VID times 1 plus the ratio of R2 over R1. Now what if VI2 is equal to 5 plus 0.005 sine omega t, and VI1 is equal to 5 minus 0.005 sine omega t. That might be a perfectly reasonable signal, and I've said before, we call this a DC bias. And we call this AC, or the signal. And it's very common. It's really absolutely totally typical that we need to have a DC bias on there, and we'd like to get rid of that. So with these values, VID, the difference between these which is equal to VI2 minus VI1 is equal to 5 plus 0.005 sine omega t minus this quantity 5 minus 0.005 sine omega t. And if I pull that out, we're going to When we simplify it, that cancels with that. But this plus is a plus, and this minus and a minus is a plus. So that becomes a plus. And we'll get VID is equal to 0.01 sine omega t. Now, the interesting thing here about this instrumentation amplifier is that V out 1 is actually going to be VI2 plus VID over R2 over R1. So this differential voltage is definitely going to be there, but we also have to add VI2 to that. So what we're going to get for V out 2 would be VI2 plus VID over R2 over 2R1, and that equals 5. That 5 volts comes back in now, plus 0.005 sine omega t. Plus, and then the differential voltage, 0.010 sine omega t times R2 over 2R1. And V out 1, likewise, I'll just write it in. It's going to be the same kind of thing. So it's going to be VI1 minus VID over R2 over 2R1. That's going to be equal to 5 minus 0.005 sine omega t minus I think that's minus a minus. Let's see. Got 1. Yeah, it's minus a minus. So minus 0.00010 sine omega t R2 over 2R1, and we'll get 5 minus 0.005. Well, no, I don't need to write that out. And so now when we take the difference of V out 1 and V out 2, what we did up here, we do the difference. So V out 2 minus V out 1 would be 5. I'm going to make a 5 look like a 6. 5 minus 0.005 sine omega t minus 0.010. Let's see. No, I got that wrong. So it's a plus. V out 2 is plus. Yep. Plus 0.001 sine omega t R2 over 2R1 minus quantity 5 minus 0.005 sine omega t minus 0.010 sine, really squishing this in, sine omega t R2 over 2R1. And again, these 5s cancel on that output. And we'll have that difference, V out 2 minus V out 1. If we add these up now, we're going to have 0.01 sine omega t plus 0.01 sine omega t times 2r2 over 2r1. And we could write that as 0.01 sine omega t times 1 plus 2r2 over 2r1. Or that difference is equal to VID times 1 plus 2r2 over 2r1, which we got before. But the big power is that we've now made something much bigger. This is much bigger than the original difference, the original signal, which was 5 millivolts, wherever I first wrote it. Oh, here we are. We had a signal of 5 millivolts, right? And by running it through these two non-inverting configuration amplifiers first, we've increased that value to 10 millivolts times this 1 plus R2 over R1. If R2 and R over R1 is just 10, then we've got 11, and we've got a tenth of a volt here instead of 5 millivolts, right? A tenth of a volt instead of 5 millivolts. It's a huge improvement, and we could have this ratio could be 100 easily. If it was 100, we have a very strong signal here. We might have something more like a volt on the amplitude of that input going into the difference amplifier, which gives us a much better shot at eliminating the common mode noise or common mode signal, whatever that is. So I'll stop there. Again, I don't have any problems now, but if there is a problem, it'll show up right at the end here.